one of the most important things the derivative can tell us is where the minimum and maximum points are on a function. So that's what the question we're going to look at today is: how do we identify the minimum or the maximum points of a function? And to set this up, there's a little bit of vocabulary that we need to be familiar with as we work with this concept. And to help us kind of visualize the vocabulary, I'm going to put a function here. Let's say it's going to start at 0. It's going to come down, come up really high, go down really low, come up a little bit, and then go towards an asymptote at 0. OK? The first vocabulary word we need to know is, what is the absolute minimum? And quite simply, the absolute minimum is the lowest point. So let's actually give this graph that we just made some coordinates here. Let's call this, we'll just make it 1, 2 up and 1, 2 down. So you can see that the absolute minimum, the absolute lowest point, is at y equals -2. It's down low at y equals -2. The other word we need to know is, as you might expect, the absolute maximum, as you might expect, is the highest point on the graph. And so the highest point on this graph is up at this top peak. We're going to call that the absolute maximum. And you see that's at a height of 2. Y equals 2 is the absolute maximum of this graph. We can kind of generalize this idea of absoluteness with what we call the absolute extrema. And that is basically just talking about both the absolute max and min together. So when I say what are the absolute extrema, I'm asking what's the absolute maximum and what's the absolute minimum. But we don't just have absolute maximums and minimums. We also have what we call local minimums, which we'll say is the lowest point in the area. So there's nobody lower around here, so we're going to call it the absolute minimum. And you'll see we've got a little dip off to the right. We can call the, we can call that the local minimum, because it's kind of a valley. It's not the lowest valley, but it is the lowest valley in the area. So that's going to be at y equals -1. And similarly, we can have a local maximum, which, as you would expect, is the highest point in the area. And the local maximum, you'll see off to the right with this little peak, is the local max. It's the highest mountain in the area. It's just not the highest mountain overall. And that one has a height of 1, so we would say that is y equals 1. And similarly, we can lump those together and call them the local extrema, which is all the local min-maxes grouped together. What's interesting about all of these points, though, is if we notice the derivative or the tangent line at each of these points is always going to be a flat line. The derivative at each of these points is equal to 0. They have a slope of 0, slope of 0, slope of 0, and slope of 0. Anytime the slope is 0, that's going to identify one of these local min or local max, and possibly an absolute min or max. We have a special name for those points. Those are called critical points. Critical points are a point where the derivative is either 0 or undefined. And what's really important there is it might be a local extremum. It's not guaranteed to be a local min or a local max, or even an absolute min or an absolute max, but it certainly is a very good candidate for that to occur. So using this idea, this leads into, getting away from the vocabulary now, this leads into what we call the extreme value theorem, or affectionately called the EVT, extreme value theorem. And basically, the extreme value theorem states that if a function f is continuous on an interval between a and b, then there is an absolute maximum on AB and an absolute minimum on AB. In other words, if we take a closed interval, somewhere on that interval is going to be a maximum, and somewhere on that interval is going to be a minimum. And what's really important to note is the min and max points are either A, the first point of the interval, B, the end of the interval, or what we're going to call C. They're either at A, B, or C, where C is when the derivative at that point equals 0, or where C is a critical point. What this is really saying is find the critical points and test these points and the edges. And either the critical points or the edges are going to be your minimums and or your maximums. Let's take a look at what we mean by that. Let's say that f of x is equal to 2x cubed minus 3x squared minus 12x plus 5. And we're going to look on the interval from 0 to 4 to find the absolute minimum and the absolute maximum in that range. Well, first we have to find the critical points, and that's when the derivative is equal to 0. because it might level off and come back down. So where is that derivative equal to 0? Well, the derivative is 6x squared minus 6x minus 12. And we'll set that equal to 0. Solving, we factor out a 6. X squared minus x minus 2. Continuing to factor, we have x minus 2 times x plus 1. And so we've got two potential critical points, 2 and negative 1. These are the critical points. That's where the derivative is 0. That's where it levels off. However, we need to be careful. All we really care about is numbers between 0 and 4. So negative 1 doesn't really help us because it's outside of the range. So now we know our critical points. We just have to test what is f of the critical point, what is f of the edge, and f of the other edge. One of those is the minimum, and one of those is the maximum, and one we don't really care about. So let's get our calculator. Let's hit y equals, clear out any function that might be in there. And let's just type our function in here, 2x cubed minus 3x squared minus 12x plus 5. And we'll hit second table so that we can enter in our own values. And let's delete out the values we don't care about. So we're interested in when x is 2, when x is 0, and when x is 4. And you see our y's are negative 15, 5, and 37. Negative 15, 5, and 37. And we can see on there that negative 15 is the minimum number. The 37 is the maximum number. We don't care about the 0, but we have a maximum of 37 at x equals 4. And we have a minimum of negative 15 at x equals 2. We've identified our minimum and maximum using the extreme value theorem, or EVT, for this function on this range. Let's try one more that might be a little more open. Let's see what happens when we say f of x equals cosine squared of x. And we're going to do it on negative infinity to infinity. It's not really a closed interval, but the extreme value theorem should still apply here. We can't check the extremes of negative infinity and positive infinity, but we certainly can check the critical points to see if there's any minimums or maximums. So first, f prime of x, the derivative. It's a chain rule, so we have 2 times the cosine of x times the derivative of cosine, which is sine. And we want to know when that derivative is equal to 0. Well, it's already factored. We just have the cosine of x equals 0 and the sine of x equals 0. First, thinking about the cosine of x on our unit circle, cosine of x is equal to 0. Cosine's the x-coordinate. It's equal to 0 at the top and at the bottom, which means x here is equal to pi over 2. And then we move a pi over to 3 pi over 2. So it's pi over 2 plus n pi's. Every pi around. And n can be any element of the integers. We'll say n is some integer 1, 2, 3, 4. Or it could be negative 1, negative 2, negative 3, negative 4. For sine of x is going to be the x-coordinates. I'm sorry, the y coordinates. And the y coordinates are 0 here at 0 and pi. So sine of x tells us that x is equal to pi plus n pi. Well, let's go to our calculator and see what we have for mins and maxes. Hitting y equals, clearing out the old function. We want to do parentheses, the cosine of x. And we want to square it. Delete out the old values for the table. And our first point is pi over 2. We get 0. Add in pi, so we've got pi over 2 plus 1 pi. We get 0 again. And pi over 2 plus 2 pi. We get 0 again and again. So what we see is each of these guys is going to give us 0 for a height. Let's try the other ones. Let's just try pi and plus n pi from our second, from the sine. So just pi is equal to 1. What if we do pi plus pi? Pi plus 1 pi. Also equal to 1. What about pi plus 2 pi? Also equal to 1. What we see is each of these always equals to 1. So we're going to have not an absolute max or an absolute min because it doesn't peak out, but we do get these relative maximums and relative minimums. So we can say the relative, or not relative, but local minimum at x equals pi, or let's say local minimum of 0 at x equals pi over 2 plus n pi, where n is an element of the integers. And we have a local maximum of 1 at x equals pi plus n pi, where n is an element of the integers again. Just to kind of see what's happening here, if I were to actually graph this, let's adjust our window. Let's go from negative 6 pi to pi. And I want to label every pi over 2. Min, I'm going to do a minimum of negative 2 and a maximum of 2. And then when I graph it, you see every pi over 2, there's either a local min or a local max. I didn't do the window I wanted, but it gets the idea here. As we get a local min or a local max every pi over 2 based on what we just found. And we know the height's 1 and the heights are 0. So that's the big idea for today, is the extreme value theorem. That if f is continuous, all we need to do is find the critical points and check the edges. And one of those is going to be the local min, or the absolute min. And one of those is going to be the absolute max. Take a look at it on the homework today. And we will see you in class to talk about the extreme value theorem a little bit more.